Inside silicon, the technology behind everything.
You know, a modern smartphone chip has tens of billions of transistors inside it. Each one is smaller than a virus. But what really changes when the industry goes from, say, 7 nanometers down to 3? And why does that one tiny-sounding shift pretty much define the future of everything, from AI to the phone in your pocket? Okay, let's get into it.
Yeah, tens of billions. Just let that number sink in for a second. We're talking about a single chip holding an almost incomprehensible city of microscopic switches, all firing in perfect harmony. The scale is just staggering, and believe me, it's only getting more complex.
So this is really the core question we're going to tackle. You see these numbers everywhere, right? On new phone launches, GPU announcements, AI company roadmaps, but they're so widely misunderstood. What are we actually getting when we make things that much smaller?
And I want to be super clear about this from the start. We are not here to talk about marketing bullet points or new features. We are going deep into the engineering reality, the physics, the economics, and the design headaches that separate these two huge moments in silicon history. Okay, so here's our roadmap. First, we're going to decode what these nanometer labels really mean. Then we'll dive into the wild physics of shrinking things this small. After that, the new rules for what performance actually is, the tough economics, and finally, what all of this means for the engineers who are actually building our future. So, first things first, let's just jump right in and tackle the biggest misconception of them all. What in the world is a nanometer when we're talking about a computer chip?
You know what most people think, and it's a totally reasonable assumption, is that the number refers to a literal physical size, like how long a transistor's gate is. But the engineering reality? Well, for decades now, that hasn't been true. It's more of a marketing label, a technology node, that foundries like TSMC or Samsung use to mark a whole new generation of manufacturing tech.
And that's the key right there. A technology node is a package deal. It's the foundry's way of signaling a major leap forward in their ability to give chip designers better performance, lower power use, and a smaller area, all at the same time. Think of it as a generational marker, not a measurement on a ruler.
And this analogy just illustrates that leap perfectly. Moving from 7 nanometer to 3 nanometer isn't like just making the same skyscraper a little smaller. Oh no, it's like you have to switch building materials entirely. At 7 nanometer, we were masters of steel and concrete. At 3 nanometer, we're fighting the fundamental weird laws of quantum physics itself.
Which, of course, leads us right into the physics of it all. This is where we get to the real heart of the engineering challenge. And this is where things get really interesting. I love this quote because it gets right to the heart of a huge problem called variability. See, at 7 nanometer, the transistors are incredibly predictable. They're uniform. They're good soldiers. They do what they're told. But down at 3 nanometer, when you're dealing with parts that are just a few atoms wide, quantum effects create these tiny random differences. Every single transistor becomes unique, a little unpredictable.
And this personality problem, it has very real consequences for designers. They have to build in bigger safety margins, just in case. They have to be way more conservative when they estimate performance. And they have to lean on these incredibly complex statistical models just to be sure the chip will even work reliably. Smaller, in this case, is definitely not easier.
And what this all boils down to is a massive flip in how chips are designed. It used to be that designers could dream up a circuit and they could just expect the foundry, to build it. But now, the insane complexity and the rigid rules of 3 nanometer manufacturing, especially with EUV lithography, tell the designers what they are allowed to build. The factory is now in charge. So you might be asking, if the physics is so hard, what's the payoff? Why do it? Well, that brings us to the new rules for performance, and the answer? Well, it's probably not what you think. Okay, take a look at this. For decades, a new node meant one thing above all else: a huge jump in raw speed, in clock frequency. But at 3 nanometers, look at that. The raw performance gain is actually pretty modest. The real superstar, the main benefit, is the massive reduction in how much power it takes to do something. The game has totally changed from how fast can it go to how efficient can it be. And here is the other big secret of modern chips. This is the real eye-opener. The transistors themselves, they're incredibly fast, unbelievably efficient. The new problem, the new bottleneck, are the microscopic copper wires, the interconnects, that hook all those transistors together. Resistance in those tiny wires creates heat and slows down the signals. That has become the biggest challenge to overcome.
And that is precisely why the most advanced chips, especially the ones for AI, are all moving toward things like chiplets and advanced packaging. Because they can't just make the chip run faster anymore, they have to get clever. They manage all that heat and performance by breaking a big chip into smaller, specialized pieces and then wiring them together in these really sophisticated 3D packages.
Okay, now let's talk about the money. Because even if you can solve all the physics problems, you still have to be able to afford to actually build the thing.
Just take a deep breath and look at that number, $20 million. And that's not to build a factory or even to pay the engineers. That is just for the stencils, the masks that you need to print one single chip design at a 3-nanometer fab. The cost to even get in the game is astronomical.
And that is exactly why you still see so many fantastic, successful products being built on older, more mature nodes, like 7-nanometer or even 14-nanometer. For most things out there, it just doesn't make financial sense to pay that massive premium for 3-nanometer. In the end, the decision is driven by a cold, hard economic calculation, not by ego.
Okay, so let's bring this all home. What does this new reality, this world of extreme physics and even more extreme economics, what does it actually mean for the engineers on the ground designing these chips?
This might be one of the single most important takeaways. In this new era, the physical layout engineer, the person who actually physically draws the transistors and wires according to the foundry's super strict rules, is no longer just a support role. They are a first-class, critical designer, because a bad layout can completely destroy the performance of a brilliant design.
So if you wanted to boil down the philosophical difference between the two, it's really this. 7-nanometer was the peak of the classic era of scaling. The rules were well understood, it was comfortable. 3-nanometer is a completely new ballgame. It is all about engineering under incredible physical, manufacturing, and economic constraints.
So what are the big takeaways? If you remember 3 things from this, make it these. First, the free lunch of getting automatic, predictable gains with every new node, that's over. Second, you can't cheat physics. Its weird quantum rules are now in charge of everything. And finally, success in modern chip design is now defined by having a deep, deep awareness of the manufacturing process itself.
And that leaves us with one final and I think pretty big question to think about. As we push up against the absolute physical limits of what we can do with silicon, innovation is of course going to continue. But will the next great breakthroughs be driven by clever engineering solutions, or will they simply be dictated by who has deep enough pockets to afford to play the game? The answer to that is going to shape our entire technological future.
Inside silicon, the technology behind everything.